Hey y'all, it's your math teacher, Mr. Boyden, back at it again today, and today we're in a brand new unit, and we're going to be simplifying, verifying, and solving with trigonometry. It's going to be really heavy on the algebra today, and one thing I want you to know right at the outset here is that it's a lot more fun if you think about these as logic puzzles rather than some kind of weird math thing. Yeah, of course they're math, but to me I think of them a lot like Sudoku in terms of the logic of them, and that makes it a lot more fun for me. So try to keep that mindset as you go through, that it's just kind of like a fun problem solving challenge we're working on. Since we are going to be learning in these first two videos about simplifying, verifying, and solving, what I thought I'd do at the beginning of the video is just start with some really basic examples, like as in elementary and middle school examples, so you can see what we mean by these terms. Here we have an example of simplify, probably pretty intuitive to you that 3 plus 5 would be 8. That's simplify. All you're doing is you're taking an expression, you're writing it in fewer terms, or today we're going to see in a lower degree would be simplified as well. What about the next one? Verify. Verify would be like the same as simplify, but you're going to do it on both sides. So now it's an equation. So like 2 plus 2 is 4, and 1 plus 3 is 4. So because we can see that 4 is the same as 4, we verified that this initial equation is true. And what about the last one? Solve. Solve's a little different. Solve, now we have a variable, and in solve, you're assuming that the equation is true, versus here, in this one, we did not assume it was true. Here, we're assuming it's true, and that allows us to do things like minus 2 on both sides. So we can get x equals 2, and we found some solution. So people say, oh, the solution is the answer. No, the solution is a value that makes the equation true when there's a variable, so we found that value here. So that's the one that's a little bit different than the other two. Simplify and verify are pretty similar. That's why today's video is going to have both of those, and it's not going to have solving. That will be next time. So let's talk about Pythagorean identities, and let's get to work. I'd like you to remember from the last unit that we learned about how cosine squared theta plus sine squared theta equals 1. Okay, that was the first Pythagorean identity, and then we had two other forms of the exact same thing. So in one of those examples, we had divided by cosine, and then we had 1 plus tan squared. If we divided by cosine, that meant that this was secant squared over on the right. And then the last one, we had cotangent squared plus 1 equals cosecant squared. So if you don't have these in front of you, even if you have them in your notes from previously, I think you need to probably write all of those down right now and have those in front of you, because what these are basically the building blocks or the tools we're going to use for simplification today. There are a couple others, but most of them we already know and they're pretty intuitive. These are ones that we kind of need to have on the tip of our tongue ready to go today for the stuff that we're going to do. So with that said, let's dive right in. Okay, we're going to try simplifying. Now, this is not quite as easy as that example 3 plus 5. That was like, well, yeah, of course, that's 8. That was super easy for us. Here we've got to think a little bit more critically. I see right here we've got a sine squared, and so that makes me think of the identity cosine squared plus sine squared equals 1. So what I'm going to do, because we know this identity is true over here, I'm going to manipulate this thing, and so it looks exactly like what I have here. So that's pretty easy. All I have to do is subtract sine squared on both sides. So minus sine squared on the right. When I do minus sine squared on the left, it'll cross that out. So now what do I have? I have that 1 minus sine squared, which matches here. 1 minus sine squared is really cosine squared. So let's make the change. So now I have cosine squared. And secant, I'm going to change secant. I remember that secant is 1 over cosine. So there it is. And so I have cosine squared divided by cosine. You simplify that out, you just get cosine x. Okay, so that's a simplified form. I hope that's a little easier to see. Like 3 plus 5 is 8. That's simplified. Cosine x is a heck of a lot more simple than 1 minus sine squared multiplied by secant. Okay, that's our first one. Let's try this one. Now, if you think you already got the hang of it, pause the video and try it. If not, then just follow along. Okay, pause as you need to. Slow down the video. If you're watching on YouTube, you can slow down the video and watch it a little slower so it's easier to track if you need to. Okay, let's remember our identity. This is jumping out at me as being really similar to the last question. So let's try to remember what the identity that had cosecant was. I think that was cotangent squared x plus 1 equals cosecant squared. And so I look at this and I say, is there a way to manipulate this to make it look like the question that I'm working on? Yeah, I think there is. So let's do minus 1 on both sides. So those cross out. I have cosecant squared minus 1. Hey, that matches perfectly. So instead of cosecant squared minus 1, we'll write cotangent squared x. and then the tan squared is still there. If you can see what's going to happen next, awesome, then you don't need the next step. If you're not sure what's going to happen next, then you will need the next step. So remember cotangent rather, that is cosine squared over sine squared. And then we have tan, which is sine squared over cosine squared. And so we have a cosine squared on top and a cosine squared on bottom, and they're multiplied, so those cancel out. And we have a sine squared on top and a sine squared on bottom, and they're multiplied, so those cancel out. What's left? Well, remember, when this is division and multiplication, you cancel things out with division. Anything divided by itself is 1. So that whole thing simplifies down to 1. Now, this work I'm doing on the right, that's really common. This is just side work, okay? I'm not actually doing the work on the question. I'm sort of doing the prep work for the question when I'm working over here on the side. And even when I work on these alone, even though I'm a little more experienced, I still always do this, okay? I just want to have all of my logic laid out nicely in front of myself so I can see what's my logical train of thought here that leads down to my simplified answer. So please actually do the side work over here like I'm doing. I think you'll find once you learn how to do these, it's helpful for organization. Let's try this one. On the outset, this one might look a little bit harder to access because, well, it's 4th degree. So let's remember a factoring technique that we learned earlier, because this is actually going to be factoring. Guys, if you haven't figured it out yet, basically right now I'm just running through a bunch of different algebraic techniques. Once you know these techniques, it'll be a lot easier to recognize what to do. So at first this might feel a little bit overwhelming for some of you, but once you figure out what I'm doing and you see all the different options, then you'll realize it's a little bit easier. Okay, so maybe if we had a question like this and we asked ourselves to factor it, that would be a little bit easier than this one. We could do x plus 3 times x minus 3. Because we'd remember that if we FOILed it back together, we'd have 3x here and negative 3x there, and those would cancel. X times x would be x squared, and 3 times negative 3 would be negative 9. You say, well, how is that similar? Well, let's build up to it. What if instead of that, it said x to the 4th minus 9? How would that factor differently? Well, here, x times x was x squared. Well, we need something that makes x to the 4th. So let's do x squared and x squared. And it would still be plus 3 and minus 3. So that brings us to the one we're currently working on. So this is kind of, guys, this isn't even side work over here. This is just me showing you how building up from an easy concept to a more challenging one, okay? So you would not be expected to show this. I'm just building up to how this works. So on this one, it's the same exact idea. Instead of x to the 4th, it's sine to the 4th. So we're going to need a sine in both of our binomials, or sine squared theta, excuse me, because if x to the 4th made x squared, sine to the 4th will make sine squared. So we'll have a sine squared here. And then we need to get cosine to the 4th, so how about plus cosine to the 4th, or squared, excuse me, and minus cosine squared. Okay, so if you need to, multiply these back out so you can see and verify that that's true. I'm just using this exact same logic right here. It just looks harder because it's sines and cosines. And here's why this is good. I look at this, and sine squared plus cosine, you may remember from our identities, that was actually 1. Either change out the sine or change out the cosine, and I don't care which one. There's multiple forms of simplification on this that work. So I'm going to start back with cosine squared theta plus sine squared theta equals 1. And then I think on this one, just because it looks easier, I will subtract over the sine squared theta. It's just what feels natural to me. If subtracting cosine over feels natural to you, then do it. Okay, so now I say instead of cosine squared, I have 1 minus sine squared. So sine squared theta minus, instead of cosine squared, 1 minus sine squared theta. And then let's simplify that out. Multiplying by 1 does nothing, so we're not going to worry about that. I have sine squared here minus negative sine squared. Minus a negative is a plus. So that's 2 sine squared theta. And then there's a minus 1 there. And that is as far as I can go, but that works. So brand new factoring technique up here, although kind of not really. I mean, we did this with quadratics earlier in the year and with polynomials. This is, I think, the first time we've done it with trig, though, so that may have looked a little bit new. What I want you to see here is that we have a fraction added to a fraction, and we need to recall that if we're going to add two fractions together, we just need a common denominator. So what we're going to do, I'm going to shift this over for a sec, and let's actually go get a common denominator. So it's going to look like this. What I do is I say, what does this denominator lack that the other one has? You say, well, they're the same, but it's a minus. That's not super helpful, unfortunately. So what I'm going to do is I'm going to multiply both top and bottom of this fraction by 1 minus sine theta. 1 minus sine theta. And then over here, I'm going to multiply by the other denominator, by this one over here. So I'm going to multiply by 1 plus sine theta on top, 1 minus sine, or 1 plus sine theta on the bottom. These two things do have to match, so you're multiplying by 1, right? And now what that's done is you can see this denominator, 1 minus sine theta, 1 plus sine theta, matches the one on the right, 1 minus sine theta, 1 plus sine theta. So now we can write out our next step. So I distribute the 1's in. Heck, that's easy. We can distribute 1's all day. So I get 1 minus sine theta plus 1 plus sine theta over, and then I'm going to multiply these together as well. Okay, and they're the same on both sides, so it's going to be the same thing. So 1 times 1 is 1, and then 1 times sine looks like a plus sign, minus sine, and a minus sine squared. All right, let's simplify a little bit more. Looks like we have plus sign and minus sign here, so those go away. Minus sign and plus sign here, so those go away. 1 plus 1 is 2. And I have 1 minus sine squared theta. Going back to the Pythagorean identities, 1 minus sine squared theta is cosine squared, so we get 2 over cosine squared theta. And we can actually go a little bit further, because remember what 1 over cosine was? If 1 over cosine was secant, this then is 2 secant squared theta. So what are the basic things that I think you should look for? I think that you should try to write out things in terms of sine and cosine. That's one trick that works. Okay, another one, if you see something squared or a higher degree, like we had examples that were to the 4th power or 3rd power, if you see something like that, it's probably a Pythagorean identity. If you see a sum or difference of fractions, like the example we did just a minute ago, then you probably need a common denominator so you can add them together. And then finally, just be creative. Try something. And sometimes the first thing you try won't work. Recognize that that's okay. If the first thing you try doesn't work, then back out. So now we're going to switch gears a little bit, and we're going to go to verifying. We did simplifying before, now we're going to verify. The thing you need to remember is that we're going to work on each side independently, meaning we're not going to add things on both sides or subtract things on both sides. We're going to do that until both sides are exactly equal. Logically, it's actually kind of similar to simplifying, or at least the steps are going to feel that way. It's just that we have two expressions we're working with, one on the left and right. So that's going to look different, but logically it should feel pretty similar, I think. So let's try this first one. Okay, the first trick was write everything in terms of sine and cosine. So let's do that here. So I have cosine x, tangent is sine x over cosine x. And then it looks like cosine can cancel on top and bottom. So what am I left over with sine x? Okay, I'm going to be a little bit lazy here, and instead of writing sine each time, I'm just going to pull it directly down. This arrow is noting that I've not modified it at all. So sine x equals sine x. Those are clearly the same. This one's done. Hey, a more interesting one. How about that? All right, now we get to have a little bit of fun. So what I notice in this one, if I start on the right-hand side, there's not very many different things I can do. The only thing I could do is I could switch sine squared out for 1 minus cosine squared. On the left-hand side, this thing looks to me like possibly it relates to an identity, so I want to investigate that first. So I'm going to recall the Pythagorean identity that has secant squared in it, and that goes like this. Tangent squared plus 1 equals secant squared. My next question is, can I modify this to match the question at hand? Absolutely I can. Just minus 1, minus 1. Now that says secant squared minus 1, and so does that, so I'm ready to make a substitution. So let's do that. And I get tan squared over secant squared. Oh, because I wrote theta, I should have written x to be consistent, so let's redo that. So tan squared x over secant squared x equals sine squared x. A common mistake people will make here is they will switch secant squared out for tangent squared plus 1. The issue with that is, if you look at the form of these two sides, see how the one on the left had subtraction and the one on the right didn't? If we change this out, we'll be introducing subtraction, well actually in this case addition, but we'll be introducing addition, and so then the operations on the two sides won't match. Right now on the left everything's multiplication and division, and so is everything on the right. So that suggests that maybe we're getting closer to our answer. So what could I do now? I could write everything out in sines and cosines, just like in example A. So let's do that. Tangent is sine over cosine. And we recall that secant is 1 over cosine. and that equals sine squared from the right side. This is just coming straight down. And then we have a fraction divided by a fraction. So let's flip that bad boy up and multiply. So cosine squared x over 1. Cosine squared on top, cosine squared on bottom, so those cancel. And so what's still left over? Sine squared on the left, sine squared on the right. All done. Cool. A really fun one. Sometimes a technique that can be helpful is we look for something that's way different than everything else. So here, this is first degree, first degree, first degree, second degree. Okay, that might be a hint that maybe something is a little bit different here. So I want to try to identify the identity that uses cotangent. So that was oops, if I wrote cosine. Cotangent squared x plus 1 equals cosecant squared x. And from here, I'm going to subtract 1, so it matches the question at hand. So I have cotangent squared by itself, just like this. Let's make a substitution and see if it works. So I'm going to write cosecant squared minus 1 over 1 plus cosecant equals 1 minus sine over sine. Okay, and this might look like a dead end. You say, wait, we started with something squared, it's still squared. However, this thing is factorable. That's a difference of squares. So recall earlier we did the example x squared minus 9, and that factored as x plus 3, x minus 3. The reason this is so easy for me to recognize is because I recognize it as a difference of squares, which goes like this. Anytime you have something squared minus something else squared, it's like x squared and 3 squared, and that's a difference because of subtraction, that will always factor as a plus b times a minus b. This is one of those rules that's sort of worth learning. Okay, it's going to be pretty useful, not only in this class, but for sure going forward in other math classes that you take as well. Okay, so I can factor this into cosecant x plus 1 multiplied by the quantity cosecant x minus 1. Still over 1 plus cosecant x. And on the right side, we still have all the same stuff. I'm not modifying it yet, so I'm not even going to write it. But what jumps out at me now is this is cosecant plus 1, and this is also cosecant plus 1, so this cancels out. And now I have cosecant x minus 1 equals 1 minus sine x over sine. So that is good, because I was dealing with something that was second degree before, and I've whittled the left sign down to a first degree, so now I've got hope. So the only thing I actually know how to do now is re-express cosecant as 1 over sine. So 1 over sine minus 1 equals, and you know what? I actually can legally write this as the exact same thing. Here's why. Because right here, this says 1 over sine, doesn't it? Looks like I forgot the x, though. I'm getting lazy on my x's. So 1 over sine x, and then right here, this says minus, so I'm going to write a minus. And this says something divided by itself, doesn't it? So that's 1. These match. We're done. All right, what about this one? You may be starting to get to the point where you feel like you could do these on your own. If you're feeling good about doing that, go for it, okay? It's always worth a try. You may get stuck. You may go down a path of logic that you have to turn around and come back from. It's totally okay. That's going to happen when you do these. Okay? Here's what jumps out at me on this one. On the right-hand side, I see 2 terms. A lot of people see 3. The reason it's only 2 is because there is a single plus or minus. That's what separates terms, is addition and subtraction. So I have a term on the left, term on the right. What do they have in common? They have a tan squared, which means I'm going to be factoring out tan squared. So tan squared theta multiplied by whatever's left over, secant squared theta minus 1, it looks like. Ooh, we just saw that a minute ago. We remember that's from a Pythagorean identity. How did that one go? That one, I believe, went tan squared, and I'll use theta so it matches, plus 1 equals secant squared. We subtracted 1. Yep, we've already done this one today. So we can start to kind of notice a pattern here. Okay, so instead of secant squared minus 1, I can write tan squared. So I write tan squared. And then secant squared minus 1 is also tan squared. And when you have tan squared times tan squared, you actually have tan to the 4th. And what do you know? That matches exactly what this does. So tan to the 4th. Now, notice on this one, I didn't manipulate the left-hand side at all. I just manipulated the right, and I was able to get them to match. What about the previous one? The previous one, I mostly manipulated the left-hand side, But at the end, I did one manipulation step on the right. I didn't have to. Really, it's whatever you can do to make these two things be equal. So your answer may differ from someone else's. What about this one? I only manipulated the left side. On the first one, I only manipulated the left side. There's not a hard and fast rule about how this works or what you're supposed to do. But that's part of the fun, is that you're going to follow what makes sense to you. And as long as you don't break rules, it's going to work out just fine. So we may start to have noticed a pattern by now. And the same pattern for simplification. If you have a fraction plus a fraction, guess what you get to do? You get to add them together. In order to do that, we're going to get our common denominator. So it looks like in this case, that's going to be 1 plus sine alpha. By the way, I'm just looking to see what the other denominator is and rewriting it over here. There's no fancy changes. There's no moving pieces. It's just literally copy and paste that exact thing over to here. Same thing on top and bottom. So 1 plus sine alpha. What about on the right side? This one has a cosine, so I'm bringing a cosine over here. So cosine alpha. And over here, we're going to multiply by cosine alpha. Let's simplify before this gets too stressful. I'm going to multiply these together on top, and I'm going to leave the bottom alone. It's just a pattern that I've seen enough times to be able to recognize that you don't need to multiply the bottom together. If you happen to multiply these together, you could always factor them back out again later in the question if you needed to. Let's do the numerator. So 1 times 1 is 1, and 1 times sine is sine. And 1 times sine is sine again. And sine times sine is sine squared. And we have a cosine squared from the right side here. That whole thing is over 1 plus sine alpha multiplied by cosine alpha. And I'm not going to manipulate the right side yet, so I'm just going to leave that alone for now. All right, what do we see that we know how to work with? All right, couple things. Right here, sine squared plus cosine squared is ding, 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 ding. That's 1. That's easy. Sweet. Sine plus sine is 2 sine. So this is going to be a major simplifying step here, okay? I've got this one and that one. That makes 2. So that would be 2 plus, and I have 2 sines, so that would be plus 2 sine alpha over 1 plus sine alpha times cosine alpha. Don't forget the parentheses. Now, notice the similarities and differences between the numerator and the denominator here. There's some pretty important similarities. So don't forget my equal sign. I'm trying to make them go vertically, but I ran out of space here and I had too much space here. Okay, so notice similarities. You got a number plus that same number of signs. 1 plus 1 sine. That means we can factor a 2 out of the numerator, so they match. So factor a 2 here, and you get 1 plus sine over 1 plus sine, that quantity times cosine. And so now those cancel out. And I'm actually going to come over here to the right because I'm running out of space over here. So I'm going to rewrite this as well. So I'm going to have 2 over cosine alpha equals 2 secant alpha. And you may recall that secant is 1 over cosine. So I'm going to leave the left side alone. And I could have changed this into secant. Again, there's lots of different ways to do this. And then on the right, I'm going to have 2 over cosine alpha because that's what secant is. So that one's done. All right, a couple more. Let's try this one. Sometimes this one can be kind of confusing because there aren't that many things that we know how to do with it. In fact, probably on the get-go, the only thing that we really know how to do with it is write it in terms of sine and cosine. So let's try that and see what happens. So we'll write this as sine x over cosine x, and we'll write cotangent as cosine x over sine x. And on the right, we'll write secant as 1 over cosine, and cosecant as 1 over sine. All right, so we look again, we say, all right, is there anything we know how to do? Not a lot, although on the left we have a fraction plus a fraction. Let's add them together. We're going to need a common denominator, so multiply by cosine on the right. On the left, we need a common denominator, so multiply by sine. And you may have already noticed that's going to make this really easy, because on the left we have sine times sine, that's sine squared. And on the right, we have cosine times cosine, that's cosine squared. And we already know sine squared plus cosine squared is 1, so this is about to get really easy. Then in the denominator, we have sine x times cosine x. So this is easy to rewrite right now. I'm not going to modify the right side yet. So I'm just going to wait for a second on that. On the left, I get 1 over sine x times cosine x, and it jumps out at me that I probably can't really modify that any further. So now I'm going to look to the right and see, is there anything I know how to modify here? Well, I got two fractions that are multiplied. I guess I could multiply them together. So 1 times 1 would be 1. Hey, that matches. Nice. And we have cosine times sine. That says cosine x times sine x. So here's the question. Are those two things the same? Because this one has sine cosine and this one has cosine sine. Yeah, guys, you can absolutely leave that, and here's why. We remember that in multiplication the order doesn't matter. Any mathematician would know that just by looking at it. So we actually can just leave this alone right now. We don't need to go any further. If you want to rewrite it so they look exactly the same, you can, but you don't have to. That's going to do it for today. I hope you enjoyed the video, and we'll see you next time.